In the last lecture, we introduced the concept of lossless transmission line. We said if the resistance and the conductance per unit length of transmission line is 0, then there are only reactive elements in the transmission line. So, there is no loss of power because there is no ohmic element in the transmission line. So, in an ideal situation, the line is lossless if R equal to 0 and G equal to 0. Then we introduce the concept of what is called the low loss transmission line, which is more practical line, where the resistive component R is much less than omega L and G is much less than omega C. If this condition is satisfied, then we said that we can treat the line still lossless. However, since the loss is very small, as and when we require the calculation of losses along transmission line, we can use the value of the attenuation constant alpha. Substituting this condition that R is much less than omega L and G is much less than omega C, we calculated the propagation constant, which can be separated into real and imaginary part, and then we got the value of alpha and beta in the approximate form. So, this quantity here is equal to beta and this quantity was represented as alpha. One would however notice that the condition which you have defined for the low loss, that is now in terms of the primary constants of the line. In the data sheet, however, for a transmission line, the primary constants are rarely mentioned. The parameters which are mentioned for transmission line are the effective phase constant on the line or the velocity on the cable, and the attenuation constant of the line either in terms of dBs or in terms of Nepers. One would then like to convert this condition R less than omega L and G less than omega C in terms of these secondary parameters or in terms of the relationship between beta and alpha. Since these parameters are available readily on the data sheet, if I can establish a condition between these elements or these parameters for low loss nature of the line, then I can find out whether a particular line is low loss at a particular frequency. So, now what we do is, starting from this relationship between beta and alpha, we can find out under what condition we can treat the line as a low loss transmission line. Taking this value of alpha, I can multiply this quantity here by square root of L in the numerator and square root of L in the denominator. Similarly, I can multiply this quantity by square root of C in the numerator and square root of L or C in the denominator. So, the alpha now can be written in terms of this substitution. So, I get this value of alpha, which is equal to half into R upon L into square root of LC. Similarly, I can, by multiplying by square root of C in the numerator and denominator in the second term, we get half G upon C into square root of LC. Multiplying numerator and denominator by omega, this can be written as half R upon omega L omega square root LC plus half G upon omega C omega square root LC. And as we have seen earlier, this quantity omega square root LC is nothing but beta. So, this I can write as beta into half R upon omega L plus half G upon omega C. Now, from the definition of the low loss, R upon omega L is much smaller than 1, G upon omega C is much smaller than 1. So, this whole quantity is much smaller than 1. So, essentially what we are saying is that alpha now is equal to beta multiply a very small quantity, or in other words, for low loss the condition now is that alpha is much less than beta. Since we know beta in terms of wavelengths, which is nothing but 2 pi divided by lambda, once we know the wavelength on the transmission line, I can find out what is the value of beta. From the data sheet, I can find out what is the attenuation constant. If it is given in terms of dBs, I will convert that in the Nepers per meter. And if this condition is satisfied, that the beta is much larger compared to alpha, then the line can be treated as the low loss transmission line. What does this physically mean? We know that if we travel a distance of lambda on transmission line, the phase change is equal to 2 pi. Let us say if I travel the distance for a lossy transmission line, then the amplitude of the wave will reduce by e to the power minus alpha into the distance travelled, which is one wavelength. So, if I consider a wave which travels a distance of one wavelength on transmission line, then its amplitude will vary e to the power minus alpha into x, that is equal to e to the power minus alpha into lambda if I travel a distance of one wavelength on transmission line. Substituting for lambda, which is beta divided by 2 pi from the previous relation. So, lambda is 2 pi divided by beta. I get here this is equal to e to the power minus alpha into 2 pi divided by beta. Since for low loss condition alpha is much smaller than beta, this quantity alpha into 2 pi divided by beta is much less than 1. That means the amplitude of the wave now reduces to e to the power minus 2 pi multiplied by alpha upon beta, and since this quantity is very small, essentially the amplitude reduction in the wave is negligibly small. So, in other words, what we are saying now is that a line can be treated a low loss transmission line provided the change in the amplitude of a travelling wave is negligibly small over one wavelength distance. Of course, negligibly small is a very subjective number. So, you can consider 1% as negligible or 0.1% as negligible. Let us say as a reference value, we consider 1% is a negligible quantity. So, when the amplitude reduces to 1% of its original value, then we say that line can be treated as a transmission line. Since this quantity is very small, essentially when this number becomes approximately 1%, that is where the amplitude will reduce by 1%. So, if alpha 2 pi divided by beta is approximately 1 upon 100, the wave amplitude will reduce by 1% over a distance of one wavelength. From here, then I can find out what is the acceptable value of alpha compared to beta. So, in practice, for a given line, there is nothing absolute whether the line is lossy line or low loss line. For a given frequency, it may be possible that alpha may be much smaller than beta, but when the frequency changes, the condition may not be satisfied and the line cannot be treated as a low loss transmission line. So, for a given loss on transmission line, depending upon the frequency, the line may be treated like a low loss transmission line or it may not be treated like a low loss transmission line. Let us take a simple example to find out what are the physical parameters which we will have on transmission line if we just take some typical line parameters. So, let us say I have a transmission line whose primary constants are given as L is equal to 0.25 microhenry per meter. Let us say the capacitance per unit length is 100 picofarad per meter. Let us say the conductance per unit length is 0 for this transmission line. So, G is equal to 0, and we want to know what should be the resistance per unit length of the transmission line, so that the line can be treated like a low loss transmission line. Let us say the frequency of operation is equal to 100 megahertz. From here, since I know the value of L and C and the frequency, I can find out what is the value of beta. So, beta is equal to 2 pi into frequency, which is 100 megahertz, which is 10 to the power 8 hertz, square root of L, which is 0.25 into 10 to the power minus 6 for microhenry, multiplied by 100 into 10 to the power minus 12 for the picofarad. This will be equal to pi radians per meter. Just to take a number, if I say that if alpha is less than 1% of value of beta, I can treat the line as a low loss transmission line. The alpha should be approximately pi divided by 100. Now I can go back and substitute this value of alpha in the expression for alpha, that is alpha is equal to half into r square root of C upon L, and if I substitute the value of C L and the value of alpha, which is pi upon 100, as you have taken 1% of the value of beta, then I get the value of R, which is less than or equal to pi, approximately 3.14 ohms per meter. So, if I accept alpha value to be 1% or less of the propagation constant beta or the phase constant beta, then the resistance per unit length of the transmission line should be 3.14 ohms per meter at the frequency of 100 megahertz. Of course, as I said, if the frequency changes, then the acceptable value of resistance will change, because the line may not satisfy this condition at that frequency. Having understood this, now as we mentioned earlier, until and unless somebody specifically tells you that the line is a lossy line, we take a liberty to treat the line as a lossless line, because as first order, as we have seen, that the phase constant for a low loss line and a lossy line is same. Also, the characteristic impedance of a low loss line is almost real, and that is same as the characteristic impedance of lossless line. So, here onwards, until and unless somebody specifically says include the losses in the calculation of transmission line, we will treat the line to be lossless and carry out all our analysis for a lossless transmission line. So, here onwards, essentially we will assume that the characteristic impedance of transmission line is given by this. So, Z0 is square root of L upon C, this quantity is a real number. Also, the propagation constant is equal to the phase constant. So, we have gamma is equal to J beta, that is equal to J omega square root L C. With these parameters, now we will again revisit the voltage and current expressions on transmission line, and then we carry out the analysis of the standing waves on the transmission line. Going back to the original equation of voltage and current, as we have seen, for a transmission line whose origin has been defined at the load point, that is L equal to 0, the voltage and current equation can be given by this. This represents the forward travelling wave, this represents the backward travelling wave, and now we will replace this quantity gamma by J beta, the x will be replaced by minus L. So, we will have the voltage and current now as a function of distance on the transmission line, and gamma will be replaced by J beta, and Z0 now is a real quantity. So, we can write explicitly the voltage and current on a lossless transmission line as, so this is the lossless transmission line. So, the voltage is V as a function of L, that is equal to V plus e to the power J beta L plus V minus e to the power minus J beta L. By taking e to the power j beta L common, the same thing can be written as V plus e to the power j beta L into 1 plus V minus upon V plus e to the power minus j 2 beta L. And this quantity, as we already know, is nothing but the reflection coefficient at the load end. So, this quantity we denote by the reflection coefficient at the load end gamma L. So, V minus upon V plus, as we have seen earlier, is nothing but equal to gamma L, which is equal to ZL minus Z0 divided by ZL plus Z0. So, now the voltage at any location on the transmission line can be given as VL is equal to V plus e to the power j beta L into 1 plus gamma L e to the power minus j 2 beta L. Similarly, I can take the current equation and I can substitute gamma equal to j beta L in the current equation, and I can get the current at any location on the line I of L, that is V plus upon Z0 e to the power j beta L minus V minus upon Z0 e to the power minus j beta L. Again, taking V plus e to the power j beta L upon Z0 common, we can write down here this is V plus e to the power j beta L upon Z0 into 1 minus, again V minus upon V plus will be equal to gamma L. So, this is equal to gamma L e to the power minus j 2 beta L. These two terms, as we know, essentially represent the forward and backward travelling wave. So, the whole expression here essentially represents superposition of the forward and backward travelling wave, which is nothing but a standing wave on the transmission line. So, here the expression for the voltage and current, they represent the standing voltage and standing current wave on the transmission line. Now, we can investigate certain features for the transmission line from here, and first thing what we will note here is that there are two terms either in voltage or current. So, you are having this term which is having amplitude 1, and then you are having a second term whose amplitude is modulus of this quantity gamma L plus a phase which is the phase of gamma L plus this quantity phase which is minus j 2 beta L. Writing very explicitly the complex reflection coefficient in terms of its magnitude and phase, let us say I define gamma L is equal to modulus of gamma L e to the power j phi L, where phi L is the phase of the reflection coefficient at the load end. Then I can write down the current and voltage explicitly in terms of this magnitude of the reflection coefficient and the phase. So, I have finally two expressions here, one for voltage which is V plus e to the power j beta L into 1 plus mod gamma L e to the power j phi L minus 2 beta L, and the current I L will be equal to V plus divided by Z0 e to the power j beta L into 1 minus mod gamma L e to the power j phi L minus 2 beta L. Now, let us see how the voltage and current varies if I measure the magnitude of the voltage and current along the transmission line. What is the variation of the voltage and current along the transmission line? So, first thing what we will notice is, as we move along the transmission line, this quantity L is positive because we are moving towards the generator. So, as I move towards the generator, the phase becomes more and more negative. So, this quantity phi L minus 2 beta L, this phase becomes more and more negative. Or in terms of the complex plane, when the phase becomes more negative, essentially we move on the clockwise direction. So, by moving towards the generator, the phase becomes more and more negative. The amplitude of this thing remains constant, this term, and total voltage will be the vector sum of this term and this term. This term is the real term, this term is the complex term whose phase is given by that and whose magnitude is given by mod of gamma L. So, essentially this is saying that this is the vector of unity 1 which represents the first term. Then I have another vector here whose magnitude is mod gamma L, and the phase of this is phi L minus 2 beta L. And as I move toward the generator, the phase becomes more negative, but the magnitude of this remains constant. That means this whole quantity represents a circle where the point moves on this circle as the L changes. So, this motion around this is toward generator. And the magnitude of this term in the curly brackets is given by the vector which is the joining of these 2 points. So, this vector. So, this is nothing but 1 plus mod gamma L e to the power j phi L minus 2 beta L, magnitude of this quantity. So, the first term is this vector which is unity, the second term is the vector which is rotating as we move towards the generator or on the transmission line, and the magnitude of the total quantity here essentially varies as we move on the transmission line. The thing to note here now is that when it moves on the circle, at some phase when this quantity is 0 or 2 pi or 4 pi, e to the power j 0 or e to the power j 2 pi or e to the power j 4 pi, that is equal to plus 1. So, I get a magnitude which is maximum, which is represented by this point, that is nothing but 1 plus mod gamma L. Similarly, if this quantity phi L minus 2 beta L is odd multiples of pi, e to the power j odd multiples of pi will be equal to minus 1. So, I will get 1 minus mod gamma L, that will be the minimum value which I will see for this term here, which is represented by this point where the 2 terms cancel each other. So, I see that the variation of voltage and current is bound by 2 limits. When the 2 terms directly add each other, that time I will see the maximum voltage. If they cancel each other, I will see the minimum of the voltage. Similarly, when these 2 terms add each other, I will get the maximum current, and when these 2 terms cancel each other, I will get minimum of the current. So, the condition when this quantity is plus 1, the voltage will become maximum, but when this quantity is plus 1, this quantity is plus 1, there is a minus sign here. So, when this quantity goes maximum, at the same location L, this quantity will go minimum. That is a very interesting thing now. Earlier when we talked about the lump circuit, wherever we have voltage higher, we also have a current higher. Now, what we are seeing here is that when the voltage is maximum, the current is minimum, and vice versa. When this quantity becomes minus 1, that time the voltage will be minimum, but this quantity will become plus. So, I will get the current maximum. Or in other words, on the transmission line, if I measure the magnitude of the current and voltages, the maximum current and maximum voltage do not occur at the same location, rather they are staggered in space. Wherever there is a maximum voltage, there is minimum current and vice versa. So, the standing wave of the voltage and current, they are shifted with respect to each other in space on the transmission line. So, if I plot the magnitude of the voltage on the transmission line, so let us say this is my transmission line, which is terminated in some load here, which is ZL, and I plot now the voltage and current on the transmission line. So, let us say I plot mod V. The mod V will have a variation which will go something like that. This is the location where magnitude of the voltage is minimum. This is the location where the magnitude of the voltage is maximum. And as we saw just now, that wherever voltage is maximum, the current will be minimum and vice versa. So, the current will go something like that. So, this is the plot for voltage mod V, and this is the plot for modulus of the current. So, this plot we are having mod V or mod I as a function of distance. This is L equal to 0 and distance is measured towards the generator. So, this location here I get voltage maximum and current minimum. When I go here, I get current maximum and voltage minimum. So, the important thing, when the standing waves are present on the transmission line, then the voltage and current waveforms are shifted with respect to each other, and maximum of voltage aligns with the minimum of current and vice versa. Having understood this, now I can again go back and look at this expression of the voltage and current. If I go to the location where the voltage is maximum, that means this quantity is plus 1, the voltage will be mod of V plus multiplied by 1 plus mod gamma L, because this quantity is plus 1. At the same location, I will have the current which will be minimum, as we saw. So, this will be I L mod of V plus divided by Z0, and Z0 is real now since the line is lossless, 1 minus mod gamma L. So, once I know the voltage and current, I can find out the impedance at this location where the voltage is maximum or the voltage is minimum, or when the current is minimum and the current is maximum. The interesting thing to note here is that irrespective of the phase of V plus, when the voltage is maximum or minimum, the ratio of V and I is a real quantity. If I take a ratio of these two, V of L divided by I of L, that is equal to Z0 into 1 plus mod gamma L e to the power j phi L minus 2 beta L divided by 1 minus mod gamma L e to the power j phi L minus 2 beta L. And when voltage is maximum or minimum, this quantity is plus 1 or minus 1. So, for maximum voltage, phi L minus 2 beta L is E1 multiple of pi, that is, it is 0, 2 pi, 4 pi and so on. For minimum voltage, phi L minus 2 beta L is equal to odd multiple of pi, that is pi, 3 pi, 5 pi and so on. So, when the voltage is maximum, this quantity is plus 1. So, Z0 is real now, this quantity is 1 plus mod gamma L, denominator this quantity is again plus 1. So, this quantity is 1 minus mod gamma L. So, the ratio of this quantity is a real quantity. So, when the voltage is maximum, the impedance seen on the transmission line is real, irrespective of what the line is terminated in. Even if the line is terminated in a complex impedance, if I move on the transmission line and go to a location where the voltage magnitude is maximum, at that location the impedance measured will be always real. Similarly, when I go to a location where the voltage is minimum, this quantity will be equal to minus 1. So, I will get 1 minus mod gamma L divided by 1 plus mod gamma L now, and again this quantity will be real. So, we make a very important conclusion now, and that is, on a transmission line, wherever there is a voltage maximum, the impedance measured is real. Wherever there is a voltage minimum, the impedance measured is real. So, irrespective of what the impedance with which the line is terminated, you will always find these points on the line where the voltage is maximum or minimum, and that location the impedance measured will be a purely real quantity. What will be the value of this maximum and minimum impedances? We can substitute this. So, at a location where the voltage is maximum and the current is minimum, that is the highest impedance you are going to measure on the transmission line. So, this quantity, when the voltage is maximum, at that location we get the maximum possible impedance which we can measure on the transmission line. So, we can get the maximum impedance which one can see on the transmission line, and let us call that as Z max. This is nothing but V maximum divided by I minimum. And since we have seen that this quantity, when you are having the voltage maximum and current minimum, that time the phase difference between them is 0. So, this quantity is a real quantity. So, Z max is nothing but R max as a resistive impedance, that is equal to, from here if I substitute this equal to plus 1, I will get equal to Z naught into 1 plus mod gamma L divided by 1 minus mod gamma L. Similarly, if I go to a location where the voltage is minimum, so this value will be 1 minus mod gamma L, but at the same time the current will be maximum. So, that is the lowest value of impedance you can see on the transmission line. So, you get the minimum impedance on the line, which is Z minimum, that will be V min divided by I max, and that will be equal to Z0 into 1 minus mod gamma L divided by 1 plus mod gamma L. So, once the load impedance on the line is known, the reflection coefficient gamma L is known, its magnitude is known. So, I know what is the maximum and minimum value of impedance I can see on the transmission line. So, as we move on the transmission line, the impedance is going to vary, as we saw, because of impedance transformation, but there is a bound on this impedance variation. The lowest value of the impedance which one can see on transmission line is Z minimum, or this is R minimum, this is resistive, and the maximum value which one can see on the transmission line is R maximum, which is given by that. Now, once we are having the voltage standing wave on transmission line, at high frequencies the measurement of phase is rather complicated. You can measure the amplitude of the signal rather reliably, but the measurement of phase is little uncertain. So, at high frequency normally we have an effort to estimate the phase not in a direct manner, but in indirect manner. By carrying out the measurements of only magnitude kind of quantities, we would like to estimate the phase of the signal. And as we have seen that the phase of the signal in time get translated into the space phase, because the total phase which we see on a wave is a combination of space and time, or in other words the phase relationship between the two waves, the forward and the backward travelling wave, that is related to the time phase as well as the space phase. And since this total phase governs the location of the maxima and minima of the standing wave, noting the location of the maximum and minimum on transmission line, one can estimate the phase which is there with the signal. So, what we do now, we define now a parameter for the standing wave, which is a parameter of only amplitude variation on the transmission line, and that quantity is what is called the voltage standing wave ratio. It is essentially a measure of what is the relative contribution of the reflected wave to the incident wave. If the reflected wave is 0, then there is no standing wave, you will have only travelling wave. If the reflected wave is full, then you will have the completely developed standing waves. So, the interference of the two waves, the forward and backward wave, is going to give me this variation of the maximum to minimum. So, we define this quantity, the value which you get for the maximum magnitude on the standing wave and the minimum amplitude on the standing wave. If I call the maximum value as V max and the minimum value as V min, then the ratio of the V max to V min magnitude is what is called the voltage standing wave ratio. And this quantity is a very important quantity, because without carrying out any phase measurement, we can measure this quantity on the transmission line. Recall, reflection coefficient is a complex quantity. So, if you want to have complete knowledge of the reflection coefficient, then we have to get its amplitude and phase. However, the quantity which we are defining now, what is called the voltage standing wave ratio, that quantity is measured by only amplitude measurements. So, by measuring the maximum and minimum magnitude of the standing wave, we get this quantity, what is called the voltage standing wave ratio Normally it is denoted by rho, which is nothing but mod V S maximum value divided by mod V minimum value. And what is the maximum value of voltage which I can see on the line? That is mod of V plus into 1 plus mod gamma L. The minimum value which I can see on the transmission line is V plus into 1 minus mod gamma L. V plus cancels. So, the voltage standing wave ratio is 1 plus mod gamma L divided by 1 minus mod gamma L. In short, the voltage standing wave ratio is called as VSWR. So, the VSWR for a load whose reflection coefficient magnitude is mod gamma L is given by this. Since the line is lossless now, the reflection coefficient at the load is ZL minus Z0 divided by ZL plus Z0, and Z0 is a real quantity for a lossless transmission line. So, ZL can have any complex impedance terminated on the line, but Z0 is real. Without much effort, then one can see that the magnitude of this quantity is always less than 1. So, the mod of gamma L is always less than or equal to 1, and that makes physical sense, because what the mod gamma L is telling you is the relative amplitude of the reflected wave compared to the incident wave. Since we do not have any energy source on the load point, the part of the energy only can get reflected. So, the amplitude of the reflected wave has to be always less than or equal to the incident wave. So, for any passive loads, the mod gamma L is always less than or equal to 1. So, in a condition when ZL is equal to 0 or ZL is equal to infinity, I will get the magnitude of gamma L is equal to 1. Otherwise, this quantity will be always less than or equal to 1. So, if I want to see very specific impedances, load impedances, for which the mod gamma L equal to 1 condition will be satisfied, I will see there will be 3 cases. Case 1 will be when ZL is equal to 0, that means the line is short circuited at the load end. So, this is a condition for a short circuited line. I substitute ZL equal to 0 here, ZL equal to 0 here. So, I get gamma L is equal to minus 1. So, in this case I get gamma L is equal to minus 1 or mod gamma L is equal to 1, mod gamma L is equal to 1, that is case 1. Second case is if I take ZL equal to infinity, that means the line is open circuited. This is open circuit line. Then again I can substitute ZL equal to infinity, take ZL first common, so it will become 1 minus Z0 divided by infinity, 1 plus Z0 divided by infinity. So, this will be equal to plus 1. So, this will give me gamma L is equal to plus 1, giving again mod gamma L is equal to plus 1. The third case is that if the line is terminated in an ideal reactance. So, the third case is if ZL is equal to J times X pure reactance, then again, so this is pure reactance, then gamma L will be equal to Jx minus Z0 divided by Jx plus Z0. This quantity in general will be complex, but the mod of gamma L will be equal to again plus 1. So, we have these 3 situations when the line is short circuited, when the line is open circuited at the load end, or when the line is terminated in a pure reactance. The mod of reflection coefficient is 1. What that means is, if the line is either short circuited or open circuited or terminated in an ideal reactance, there will be full reflection from the load end. And that makes sense, that since I am having short circuit or open circuit or pure reactance, there is no energy absorbing element available at the load end of the line. Neither short circuit can absorb power, nor open circuit can absorb power, nor ideal reactance can absorb power. So, whatever power the travelling wave takes to the load end, there is no option but to take the entire power back in the reflected wave form. So, whatever wave reaches to the load end, that completely gets reflected if any of these 3 conditions are satisfied. And that is what essentially is represented by this, that the magnitude of the reflection coefficient becomes equal to 1. That means the entire energy which reaches to the load end, it gets reflected. So, what we see from here is the reflection coefficient is always less than 1. It becomes equal to 1 in the special cases, that is short circuit, open circuit or ideal reactance. Otherwise, the magnitude of the reflection coefficient is always less than 1. If I now substitute this into the quantity which we have defined, voltage standing wave ratio, this quantity mod of gamma L now is less than or equal to 1. So, in the best case, when this quantity is 0, we will get a VSWR equal to 1, otherwise this quantity will be always greater than 1. So, as we got the upper bound on reflection coefficient mod gamma L, we can also define the bounds on the voltage standing wave ratio VSWR, and that is when mod gamma L equal to 0, the VSWR is equal to 1. However, when mod gamma L goes to 1, that time this quantity is infinity. So, we have VSWR rho, its bounds are 1 equal to or less than equal to infinity. And which is the better case? Mod gamma L equal to 0 represents no reflected wave on transmission line. That means we have full power transfer to the load. So, mod gamma L going to 0 is the best case as far as the reflection is concerned, or in other words, when VSWR is equal to 1, that is the best case for the power transfer on the line. As the VSWR increases, it indicates higher and higher value of mod gamma L, that is higher and higher reflection on the transmission line or less and less efficiency of power transfer to the load. So, in every circuit design, our effort is to make the VSWR as small as possible or as close to 1 as possible. Higher the value of VSWR indicates more mismatch on the transmission line or higher value of the reflected wave on the transmission line. So, this quantity VSWR is one of the very important quantity in the measurement at high frequencies. Whenever we design a circuit, we essentially try to measure the VSWR on the transmission line, and we try to make the VSWR as close to 1 as possible, making sure that the circuit is efficiently transferring power to the load end of the line. Once you have defined these parameters now, rho, then one can relate this rho to the maximum and minimum impedance which one can see on the transmission line. We have already seen that the maximum value of the impedance which we can see on the line is R max is equal to Z0 into 1 plus mod gamma L divided by 1 minus mod gamma L. But now we know this quantity is a measurable quantity, and that is nothing but the voltage standing wave ratio rho. So, the maximum value of the resistance or the impedance which I can see on the line is nothing but Z0 into the standing wave ratio rho. Similarly, the minimum resistance which I will see on the line is, this is 1 upon rho. So, this is equal to Z0 upon rho. So, I get from here R max is equal to Z0 into rho, and R min on the line is equal to Z0 divided by rho. So, for any line which is terminated in arbitrary impedance, if I move to a location where the voltage is maximum, then I know the value of the impedance at that location, because measuring the voltage maxima and minima, I can find out the value of this voltage standing wave ratio rho. I know the characteristic impedance on line a priori, so I know the maximum value of the impedance which a line will show. Similarly, at the location where the voltage is minimum, the impedance measured will be R minimum, and that will be the characteristic impedance divided by the voltage standing wave ratio. If you recall now, we had mentioned that if the impedance is known on any point on the transmission line, then you can always transform that impedance to any other location on the transmission line. Immediately then it strikes to us that knowing the location at the voltage maximum or minimum, the impedance value is known there. So, I can now transform either side of a transmission line towards the load, so that I can get the load impedance. This now essentially opens a measurement technique for the unknown impedance. At high frequency, if you are having a complex impedance, its measurement is quite tedious, because we cannot measure the phase very accurately. But now I have a mechanism of measuring the phase indirectly. As we already mentioned, the phase gets reflected into the standing wave pattern or the location of the voltage maxima and minima. So, if I measure the voltage standing wave ratio and the location of the voltage maxima and minima, I can always transform this impedance R max or R min to the location of the load, which is nothing but the load impedance. So, if I transform from the load impedance to voltage maxima, I will get these impedances, but I can work backwards and say, if I know the location of the voltage maximum from the load, I know the value of impedance at that location, I know the distance of load from that point. So, transformation of this impedance to the load end should give me the load impedance. When we go to the application of transmission lines, we will see that this technique is used for measuring the complex impedances, and that time we will explicitly derive the expression for the unknown impedance which is terminated to a transmission line.